Why is it that some of the most stable bonds in nature, the ones holding carbon atoms to a benzene ring, can be swapped out so easily, yet only if we use a specific nitrogen-filled bypass? Normally, if you try to replace a hydrogen atom on a benzene ring with something like a chlorine or bromine atom, the chemistry can be stubborn and unpredictable. But in 1884, Traugott Sandmeyer discovered a chemical trapdoor that changed synthetic chemistry forever. To understand how this works, we first need to look at our starting material, an aniline molecule. This is just a benzene ring with an NH2 group attached. But notice how tightly that nitrogen is bonded to the ring. To get it to leave, we have to make it want to go. The first step of the Sandmeyer reaction is diazotization. We treat the aniline with nitrous acid at freezing temperatures. Watch what happens to that amino group. It transforms into what we call a diazonium salt, a nitrogen-nitrogen triple bond. This is the key. You're looking at what chemists call the world's best leaving group. Why? Because those two nitrogen atoms are essentially a pressurized molecule of nitrogen gas just waiting for an excuse to fly away. But here's the puzzle. Even though the nitrogen wants to leave, the bond to the carbon ring is still surprisingly resilient. It needs a push. This is where Sandmeyer's genius comes in. He introduced copper-1 salts into the mix. Let's look closer at the molecular dance happening now. You might expect a simple swap, but the mechanism is actually a bit more radical, literally. As we add the copper-1 chloride, the copper atom approaches the diazonium ion and performs a single electron transfer. It donates one electron to the nitrogen. This destabilizes the entire structure. Notice how the nitrogen gas suddenly bubbles out of the solution and escapes. What's left behind on the ring is an aeroradical, a carbon atom with a single unpaired electron, desperately seeking a partner. This radical is incredibly reactive. It immediately grabs a halide atom from the copper complex. As you can see in this final transition, the chlorine or bromine snaps onto the ring, and the copper-1 catalyst is regenerated, ready to go again. And just like that, we've accomplished the difficult task of placing a halogen precisely where we wanted it. The beauty of the Sandmeyer reaction isn't just that it works, it's that it's a masterclass in chemical leverage. We take a stable molecule, turn it into a high-energy spring-loaded nitrogen group, and then use a single electron from a metal to trigger the release. Next time you look at a complex pharmaceutical or a vibrant synthetic dye, remember that many of them only exist because we learned how to use a tiny copper spark to let a little bit of nitrogen gas go free.